Another way to find delta H, we've talked about measuring it experimentally, that's calorimetry, or we can infer what it is using Hess's law, what we were just talking about. We can also calculate it from tabulated standard enthalpies of formation. So delta H is the change in enthalpy, and so we can decide where we want to be zero. Like altitude, right? Altitude, we're looking at the change in altitude. Why is zero elevation sea level? Why isn't zero the center of the earth? Well, it wouldn't be very convenient, would it? Especially before they figured out how to measure how far across the earth was. They picked sea level because it was easy. It made things easier. So they choose that to be zero. And it doesn't matter because we're just looking at the change in it anyway. So here we can define zero to be something convenient. So we're going to measure enthalpy changes relative to pure elements in their standard states. So just the regular element in whatever state it's most comfortable in, we're going to call that zero, and then we're going to look at changes in energy when we do stuff with those elements. So the standard state is just a set of defined conditions. So if we're talking about a gas, we're talking about the pure gas at 1 atmosphere of pressure. If we have a liquid or a solid, we're looking at the pure substance in whatever its most stable form is at 1 atmosphere and whatever temperature we're interested in, usually room temperature, which they call 25 degrees Celsius. If we have substances in solution, then we're going to look at that solution with a concentration of 1 mole per liter. So those are the standard states. The standard enthalpy change, delta H, now it's got this degree symbol, that means standard, is the enthalpy change when all the reactants and products are in their standard states. If we want to talk about the standard enthalpy of formation, so now we've added a subscript F. So this is the enthalpy or heat at standard conditions of formation. That's the enthalpy change for making 1 mole of a pure compound in its standard state. It's also sometimes called the standard heat of formation. So the elements have to be in their standard states, and we've defined elements in their standard states as zero. So the heat of formation for a pure element is zero, because that's where zero was. We didn't have to do anything to it. And we're going to measure enthalpy changes relative to those elements in their standard states, just like we measure altitude relative to sea level, because it's easier that way. So this is a table from chapter 7 that gives some of these standard heats of formation for different compounds and elements. So just starting at the top here, so here's bromine atoms, and bromine molecules. So both of these are just the element, it's not a compound. But what's the most stable state for bromine? Bromine's one of the diatomic elements. It's more stable as Br2, and Br2 is a liquid at room temperature. So that's the standard state for bromine, and its heat of formation is zero. You can go through the heats of formation and find the standard states by finding the ones that are zero. So for carbon, the standard state is graphite. So we can look at all these different ones, and then there's bigger tables in the appendix, and then there's even bigger tables in the CRC. Okay, so let's learn how to write formation reactions. So what we're doing here is we're looking at the elements in their standard states combining to form 1 mole of the compound we're interested in. And then that'll be the standard heat of formation for this compound. It will be so these have been measured. So if you're not sure what the standard state is, you can find the one that has delta H 0. Because by definition we're making 1 mole, we may end up with fractional coefficients here. And the units of delta H now become kilojoules per mole because the reactions are always written for 1 mole. So if we look at the formation reaction for reaction between carbon and oxygen to make carbon monoxide. So we're trying to look at the formation equation for carbon monoxide. So here's carbon monoxide, gas, 1 mole of it, and the elements that are in there are carbon and oxygen. So we think about it, or we go look up in the table, and we find out which form of carbon has a heat of formation of 0. Well, that's in its solid state in graphite, because the table told us so. And if we look up oxygen, it's going to be O2, which should make sense because it's a diatomic element, it's a gas at room temperature. Okay, but now this is not balanced, is it? When we balance it, we have to keep the coefficient of the product 1. So let's just jump back here. How would we normally balance this equation? Well, I've got 2 oxygens here, so I'd put a 2 over here, and I'd put a 2 over there and call it good. But these have to end up with 1 mole. So we can't do it that way. So for 1 mole of CO, that means I need half of an O2 molecule. So sometimes we need to do fractions here for the reactants. And we look up delta H in the table, it's minus 110.5 kilojoules per mole. That's just back in table 7.5. Any questions? Yes. Why is it 1 oxygen over here? No. Or here? So it has to be the element in its standard state. And the standard state of oxygen is not individual atoms. You can have oxygen as individual atoms, but that is not what it normally is. It would require energy to make them that way. So it has to be the element in its standard state. It would balance much nicer if it was just O. But. Okay, we'll practice. Write equations for the formation of sodium chloride and lead nitrate from the elements in their standard states. Include the values of the standard heat of formation for each equation. Well, let's do the first one first. The train agrees with me. I thought that was agreement, but maybe it's not. So the product is going to be 1 mole of sodium chloride solid. So NaCl solid. And then I look at, well, what are the elements in there? Well, there's sodium, and there's oxygen. These formation equations do not describe how these compounds were actually formed. So we need to know, yeah, what? Because I'm out of my mind. Yeah, great question. Why is there oxygen there when it's sodium chloride? Yeah, I guess I was thinking about the train. I don't know. Thank you. Okay, does that look better? Okay. So we need these to be in their standard states. A lot of these we should be able to do knowing which elements are diatomic and knowing the colors of things on the wall periodic table. So sodium, is that diatomic? No. And what is its state at room temperature? It's black on the periodic table. So sodium is a solid. It's a metal, so that kind of makes sense. Is chlorine diatomic? Yes, it is. And what is the state of chlorine at room temperature? It's a gas because its symbol is red. So this is a gas. So I've got the standard states, or you can go to the table and look for them. Now I need to balance it without putting any other coefficient here. So I have one sodium on each side. Bless you. I need one chlorine over here, but I have two there. So I need half of the pair, right? I need half of this. And then we're supposed to write a standard heat of formation for the sodium chloride. Well, we're going to go to the table and look for it. So here we have NaCl solid minus 411.2. So this is minus 411.2 kilojoules for every mole of sodium chloride that's formed. Okay? It's doable. It's a little weird, but it's nothing too crazy. Okay, so let's do this other one. So we've got Pb, NO3, 2, solid. So we can look at the letters in there and we see that there is lead, which will have some state. And there's nitrogen. That's not a very good nitrogen. Oops. And oxygen. I'm just leaving spaces for the states. Is lead a diatomic element? No. What is its state at room temperature? That's a solid. Is nitrogen diatomic? Yeah. And what's its state at room temperature? Gas. We're all breathing it right now. Is oxygen diatomic? Yep. And oxygen is also a gas. So those are our standard states. And now we need to balance the equation. Again, having a coefficient of 1 over here. So there's one lead here. So there's one lead over there. So that's good. How many nitrogens are in this compound? 2, right? And I've got 2 over there. So far, so good. How many oxygens are in here? 6. And over here, they're coming in pairs. So I need to multiply by 3. That one didn't have any fractions. Yay. And then we need to find delta H. Well, this one isn't in table 7.4. We can look, and I don't see lead in there, do you? Come on. There it is. So these are from the appendix in the back of the book. So here we have the section that has lead compounds, and here is lead nitrate, PbNO3 solid. It's got to match up exactly. Now, there's more information here. We're just talking about delta H, standard F. There's also a delta G and an S, and that's for Chem 1B. This book is used for Chem 1B as well, but we're not going to look at that. We're just looking at the first column. So my answer is going to be minus 451.9. Minus 451.9 kilojoules per mole. Any questions? Yeah. Yes. I had to put this half in here so that I could balance the chlorines and still have 1 mole of the product. If we're thinking about individual molecules, we're like, but you can't have half a molecule. But if you're talking about moles, you can have half a mole of molecules. And these things never happen with individual molecules. Right? Nobody'd be able to witness that. Any other questions? Yeah.
Is using half when you're balancing chemical equations, is that something that you can do?
It is something that you can do. You can use fractions to balance chemical equations. When you are instructed to balance an equation, like on an exam or a worksheet or something, a properly balanced chemical equation will not have fractions in it. And all of the coefficients will be the smallest possible. So if they're all divisible by 2, you need to divide them by 2. Now, can we manipulate them and do different things with them and end up with something at the end? Yeah. And the reason the fractions are here is because we want all of these to be for 1 mole of the substance. It makes things easier later on. Good question. So that heat of formation corresponds to forming the compound from its elements in their standard states. You take the elements and you go to the compound. You get delta H. Well, if you take the opposite sign of delta H, what does that represent? Going the other direction, right? So the negative of that would be taking the compound and taking it apart back into its elements in their standard states. Okay? You put it together, it's this much. You take it apart, same amount, but negative. This is the buying, selling business, right? $10 to you, $10 to me, goes back and forth, but the money doesn't like disappear in between us or get bigger or something. So we can calculate the enthalpy change for any reaction by, in our heads, taking the reactants apart into their elements. That would be the negative of delta H formation, and forming the products. You can also do this by taking those formation equations and manipulating them like we did when we were talking about Hess's law until they add up to the reaction that we want. But because of how they're defined, we don't actually have to do all of that. So for a reaction, the standard heat of reaction, we're going to take the coefficient of one of the products times its heat of formation, and we're going to add the coefficient of the next one times its heat of formation. So we'll take all the products, you take their delta H's and multiply by the coefficient. Because delta H is per mole of the compound, and if we have 2 moles, then we have twice as much heat. And these are going to be whatever delta H is, we're not changing the sign because we're thinking about making the products, which is what the heat of formation is. It's the heat involved in making the product. Then we're going to subtract the same kind of thing for the reactants. It's subtracting because we imagine taking the reactants apart. So delta H changes sign. Again, it's the coefficient times the heat of formation for each reactant. So this capital sigma means the sum of. So we take the sum of the coefficient times the heat of formation for each product, we add all of those up, and we subtract the sum of the coefficient times the heat of formation for all of the reactants. So here we are looking at the combustion of methane. That's this equation up here. We're trying to figure out, well, what's the standard heat of formation for that reaction? Well, we can look at it like this, where we've got, here are our products. We're starting here, and we're going to decompose. CH4 is going to be decomposed into its elements in their standard states. So carbon and hydrogens. And oxygen is already in its standard state, so we'll just leave that alone. So going up here, we've got the decomposition of methane. So the heat of formation for methane is negative 746. That's when you make it. So when you break it, it's going to be opposite in sign. So now we've got all the elements in their standard states, and we're going to start putting things back together. So we're going to form CO2. Well, forming CO2 is this much energy. And then we're going to form 2 moles of water. So that's the heat of formation per mole of water times 2. And we add all those together, and we get this. So you can take these equations and maybe highlight them and manipulate them like we did before, or we can do it like this. So the standard heat for this reaction is the sum of the products minus the sum of the reactants. And that's just, kind of my shorthand. I remember having a hard time remembering, well, which one is supposed to be first and which one's last? What does a delta mean? Change in. When we calculate it, it's the final minus the initial. So this is the final, the products minus the initial. So in this equation, I have 1 mole of carbon dioxide. So 1 mole of carbon dioxide times the heat of formation of carbon dioxide, kilojoules per 1 mole. And my other product is water. I have 2 moles of water, and the heat of formation for water is minus 241.8 kilojoules per mole. So those are my products. And then I'm going to subtract the reactants. So I've got CH4. I have 1 mole of CH4, and the heat of formation for CH4 is negative 74.6 kilojoules per mole. And then I have 2 moles of oxygen. They're not showing the heat of formation for oxygen here. If you forget, you can go look it up in the table, and you'll see, oh, it's 0. That's right, because it is in its standard state. So that's, 2 moles times 0 kilojoules per mole. I'm subtracting all of those. So that's where the switch in the sign comes in. Okay, so I've got negative 393.5 plus 2 times negative 241.8 minus the quantity 1 times negative 74.6 plus 2 times 0, close the parentheses, negative 802.5. Same as over here. I put these in here, all the units in here, to show you how all those moles go away. When I write this out as a calculation, I'm just going to write 2 in kilojoules. But this is what the units are really doing. So this is actually faster than writing out all those equations and turning them around and multiplying by stuff. But it's the same idea. Any questions? We have 2 examples here, and then we're done. The thermite reaction in which powdered aluminum reacts with iron oxide is highly exothermic. There's the reaction. Use standard enthalpies of formation to find delta H, the standard heat of reaction for this thermite reaction. So what we want to do is we want to find the heats of formation for every reactant and product. Do we have to worry about aluminum? No, because that's a that's an element in its standard state. Do we have to worry about iron? No, it's an element in its standard state. So we just need to look these 2 up. Oops. Okay, let's see. Aluminum, it was aluminum oxide, right? Al2O3 minus 1675.7. And the other one was Fe2O3. Let's see if we can find that one. It was this one. Fe2O3 minus 824.2. I'm writing these on the board because I'm not going to remember those in 2 seconds. Yep, don't remember them. Okay. I'm lucky I remember which compounds to look up. So, to calculate the standard heat of reaction, I'm just going to write it like this again. This is the sum of the products minus the sum of the reactants. And that's not the official way to write it out, but that's enough to jog your memory, hopefully. So I'm going to look at my products. I have how many moles of Al2O3? I have 1, right? So I have 1 times the heat of formation of Al2O3. Oh, I know what I meant to do. I meant to write this up here. So I have 1 mole of Al2O3 times its heat of formation. And then my other one is an element in its standard state. We can ignore it, or we can say, well, that's 2 times 0. So there are my products. And I'm going to subtract the reactants. Well, the first one is 2 aluminums. Well, it's 2 moles of aluminum, but the heat of formation is 0. Plus 1 mole of Fe2O3, which is minus 824.2 kilojoules. And I highly recommend using the brackets along with the parentheses because those squirrely negative signs. And you can type it in on your calculator exactly the way it looks here. 1 times negative 1675.7 plus 2 times 0 minus the quantity 2 times 0 plus 1 times negative 824.2, close the parentheses, equals negative 851.5 kilojoules. So for this reaction, as written, the standard heat of reaction is negative 851.5 kilojoules. This is different, right? I told you it was something different. I didn't say it was going to be good. Here's another one, back to those chemical hand warmers. This is the reaction, Fe plus O2 to make 2 Fe2O3. Calculate the standard heat of reaction and calculate how much heat is produced from a hand warmer containing 15 grams of iron powder. Well, to calculate the heat of reaction, we're going to do the sum of the products. Now I'm getting really lazy. Sum of P minus sum of R. Well, what's my product? Fe2O3. Oh, how convenient. That was in the last one, and I still have it written on the board. So the products would be 2 times 8 minus 824.2 kilojoules. Minus the reactants. Oh, those are elements in their standard states. So that's going to be big 4 times 0 and 3 times 0, which is still just 0, right? So the standard heat of reaction for this then is 2 times negative 824.2. Negative 1648.4 kilojoules. Now the next question, 15 grams of iron, how much energy, how much heat? The 15 grams of iron. That's a stoichiometry problem. Grams to moles to moles to grams. We're starting with grams of iron, but we're going to energy. So we just have to go to moles of iron, and then I don't know how I did that. Then we can skip directly to kilojoules. $15 grams of iron. I'm going to convert that to moles of iron, and then I'm going to convert that to kilojoules. I want to divide by grams of iron here, so the units cancel out, and divide by moles of iron here, because the units cancel out. The relationship between grams and moles is the molar mass, and for iron that's 55.85. It's just on the periodic table. And then this is the standard heat of reaction that we just calculated. So it's that many joules for how many moles of Fe2O3? For 2. So I have to put a 2 down here. So 15 divided by 55.85 times negative 1648.4 divided by 2, I often forget to do that. Negative 221.36 kilojoules, and it looks like 3 sig figs. Negative 221 kilojoules. If this is a mastering chemistry question, and you enter minus 221 kilojoules, it'll tell you you're wrong. Because this is like saying, I paid minus $10 for the shoes. Paid tells the direction, and minus tells the direction. And so it's kind of a double negative. We're talking about how much heat is produced. That tells the direction. So then we don't want to have a sign on the number because the direction is already specified. So we can say 221 kilojoules are produced. Yeah.
Shouldn't it be 4 moles of iron?
That's a good question. Shouldn't it be 4 moles of iron? Well, we're not converting moles of iron to moles of anything else. We're converting grams of iron into moles of iron. The coefficient part, oh, you mean down here? Yeah. Yeah, you're right. What? I'm losing it. Actually, I can't lose it because I already lost it a really long time ago. Thank you. Okay. Well, let's just do this. So I need to divide that by 2 again. Negative 110.68. So I would say 111 kilojoules are produced. Thank you for catching me. I need a safety net. Any questions? End of chapter 7.